my name is Emilia. I'm a member of the Harvard Biodesign Lab, and I'm going to be presenting you some of our work on wearable robotics. And more specifically, I'm going to be talking about our most recent project, Reachable, which is a device for restoring upper arm function after a stroke. So I'm just going to give a little bit of background on who we are. So we are an interdisciplinary group of roboticists, engineers, industrial and apparel designers, physical therapists, and industry professionals who have all come together to work to build and design robots and medical devices that are really intended to interact and cooperate with humans. And the main focus of our lab is wearable robots for those who are disabled, as well as able-bodied people, for example, industry workers. And then we also work to design tools for non-invasive diagnosis and treatment of diseases. So here I have just a couple images of some of the projects our lab has worked on. As you can see, we actually cover a broad range of parts of the body. So see if I can do this. In this image here, you see we have a shoulder support through inflation system. And then over here, we have a cable-driven back exosuit. Both of these projects were intended to be used by industrial workers to help prevent workplace injury. And then these two projects, this top one here is called the grip glove, and this project down here is called the community ankle. And both of these projects were intended to be for stroke patients to help restore movement in their respective limbs after a stroke. And then stroke patients are the primary medical group that we currently work with. So I'm just going to give a little bit of a blurb briefly about who I am in the lab, because I think my position is a little specific, and also I think knowing it kind of gives some context for the rest of this talk. So I'm what they call the functional apparel designer. And so basically my main role in the lab, in addition to actually building all the soft textile exosuits, is also figuring out how we're going to take this very technical piece of equipment and actually make it usable in people's lives. How is it going to integrate into their everyday routine? How are they going to put it on? These are the sort of questions I deal with. And I just thought for a little bit of a fun kind of thing, I was going to throw up some of my previous work to kind of show what I mean also in functional apparel in different contexts. So I previously was working as an intern at the NASA Soft Goods Lab, where I was designing clothes for astronauts to wear in the International Space Station. So some of the things I had to think about there is like, how do you get dressed in microgravity? Or my favorite slightly gross story is they wanted me to look at feet, because actually in space, people use their feet to like hold on to things. And what happens when you do that is all the calluses fall off the bottom of your feet and start forming on the top of your feet, and they rub raw. So they're like, please make us something comfortable to wear on your foot. So how I like to think of myself is solving engineering problems through textiles. That's basically who I am. So yeah. So back to Reachable. So the main goal of our project is to help restore upper arm function after a stroke. So in the US right now, there are about 7.6 million people who have had a stroke, 5 million of which have had some sort of lasting upper arm extremity impairment. So yeah, when you have a stroke, basically what happens is that you lose a lot of functionality in one side of your body. And it also can be extremely varied from person to person. Some are more severe than others. And really the only way to help build back your functionality is to have a high level of rehabilitation built into your life. And our goal of our project is to help build that rehabilitation into people's lives. So our proposed solution for doing this is a wearable system that can be worn throughout the day and help people by providing a little bit of support to their arm so that they are encouraged to use it to do everyday activities throughout their life. And our soft wearable robotic system is composed of two main components. There is first the soft wearable robot, which is a wearable device that goes on the arm and has what we call the actuator underneath it that inflates the arm to provide support. And then there is, with that, a digital therapeutic app that through motion sensors on the robot, tracks your movements, tells you about the quality of the movements, and then also prompts you to do more movements. And here I just wanted to give a brief shout out to this whole team. So I'm the one representing today, but this is the effort of many people with a huge range of expertise coming together to solve this incredibly multifaceted problem. So here is actually the current version of the reachable system itself. It is has three main areas of focus. So first there is the hardware box that's run on the back that holds the inflatable system as well as all the essential electronics. There is the wearable component, which is the self-donnable harness, and that's what I work on. And the main function of this is figuring out how the actuator is going to interface with the body and also how it controls how the forces are delivered to the body as well. And then there's the sensing system and the soft actuator, which detects what the user is intending to do and then inflates the actuator to the appropriate level to provide the support that's necessary. So now I'm going to briefly talk about the robotic control system that we use. So one of the really things that I think is very interesting about this problem of having to control the robot is that stroke patients do not move in the way a healthy patient might. The movements can be very erratic and they can be very different. So there's a lot of difficulty in figuring out how do we predict what the user wants to do with their movements. So the way they've done this is we use the residual motion, so whatever they are able to do, and we train a machine learning model on them to feed using the motion sensor and compression sensor data to sort of understand and know the patterns of that individual person, and then be able, based on those patterns, to predict what they want to be able to do. And then once we know what we think they want to do through the detection model, we then have a physics model that tells us, okay, at this pressure, the actuator will reach this angle, and we say we want to reach this angle, we inflate it to this pressure, and then it inflates the actuator. So that is how that model works. And now I'm going to talk more about the self-donnable harness. So this project was started 2019-ish, and through 2019 and 2023, this is what it looked like. And the last year or so, it has now evolved into this, and that's the work I have been primarily involved in. So the version of the device that existed until 2023 was what we call like a research grade version of the device. So the intended purpose of this device was just to test this idea: does inflating the shoulder system in this way provide the support that we want in the ways we want it? And one of the main reasons we had to test this is our lab is really interested in working with soft robotics versus like rigid exosuits. And the reason we do soft robotics, for the upper body instead of rigid exosuits is because rigid exosuits, well, they provide the forces like more accurately and they can transfer more. The shoulder is such a complicated joint that it's really difficult to get a rigid thing to mimic all the movements it can do, where a soft one is much more flexible in its ability to kind of do these sort of complex sweeping motions. If I push the button, will it play the video? Yeah, okay. You can see. And so what we found using this research grid version of this device was that it was really promising in terms of providing shoulder support. But there were some limitations in this next move of transferring it into people's lives. One of them being that there were some restrictions in the mobility. It tended to push you out a little bit, and we wanted it to be a smooth, clean motion to the front as well. This current version of the device could not be put on independently. People required assistance because the sleeves were difficult to get through. And then also there was a zipper in the front, which requires dexterity of the hands. And once the shirt was on, it was a little bit difficult to adjust. And then also you can kind of see in the corner, the control box is fairly large and people don't want to carry it around. We're like, that makes sense. So what we did now, oops, some of the text has moved a little, but once we had this research grade version of the device, the next step was taking it to people and getting their feedback, and not just any people, stroke patients specifically. So some of the feedback we got from our clinical studies that we brought people in, but we also would hold these focus groups where we had people come in and we'd show them low fidelity prototypes and get their feedback on what would be important to them to have this device function. And you'd get one of the most resounding things is that I needed to be able to don this with one hand. So now this is what the device currently looks like. As you can probably see, I have moved from a more shirt-like design to a more harness-like design. And this is because I wanted to get rid of the sleeves that people were having their difficulty putting their arms through and have these wide armholes. Having a more rigid structure, although it's still very soft, was better though for transferring the forces from the actuator instead of having it like pull on a knit. And then I've also moved towards these magnetic fasteners that can be used with one hand. And I completely eliminated the sleeves that you see because people had difficulty getting them on, but I needed to still interface the actuator with the upper arm. So I did this by having a cuff that can be opened and then closed. And there was the video of me putting it on. And then in addition to kind of the main features of putting on, there was also a lot of features of thinking about then the adjustment afterwards. All these adjustments needed to be done with one hand. So how do you do that? So I have these like kind of cable things to pull on the shoulders to kind of cinch it closely. And then there's cables that run for now like this, and they need to be able to be removed and put on by somebody with one hand, because what if you want to wash the device? So these are the sorts of problems solved. And right now we are taking, oops, I forgot there's another video here that's not showing, but now we are taking this device back to testing again and that's just part of the design process. You know, you make something and you go back, you keep going until you really feel like you've got the end thing. And right now we have people trying it. I am working on a one-sided version of the device just because stroke only affects one side. Do we need it to be two-armed? That's what we're working to solve. Oh, maybe it was going to play. Oh, whatever. Great. And finally, I just wanted to share one particular case study we worked on. So this is Dr. John Goodson, and he approached us. So he had been a participant in our clinical study, although he has ALS. And he had approached us to ask if we could maybe make him something to help him eat independently. And we said, we will do our best. So over the course of 2 months, we co-designed with this user. He would come in every couple of weeks and we would show him updates we'd made to this device. And at the end of those 2 months, we were able to give him a device which he has been using to eat on his own for about 4 months now. So some of the changes we made to this device was our IMU system was not yet ready to be, or the motion sensor system was not yet ready to be at home and used rigorously. So instead we made him a foot control air pump, because that is where he was able to, what movement he was able to control. And then I also made it so that the harness itself could open at the shoulders, because John cannot independently dress himself. So instead I was thinking about how I can help the caregiver he lives with. How can I make it easy for him to dress John? And what we really learned from this was that, this device, even the simpler version of this device, has a really strong potential to make difference in people's lives. And that also this device might be interesting to people beyond stroke, that with changes and modifications, there are other groups that might find this device interesting as well. Thank you.
Yeah, so I don't know if there's, oh, you have a question back there.
That's so creative. Thank you for sharing those designs with us. So what about for a disease that's progressing? You know, when someone's had a stroke, oftentimes you envision them staying the same or getting better, but in FSHD, you might have a progressively worse disease. And so how would you design for that?
Yeah, no, that is a really good question. Sorry. Thank you. That's a really good question, and that's definitely one of the areas of interest, because, you know, as you pointed out, this device is intended for rehabilitation after stroke, and thinking about for a disease. So with John for ALS, that was definitely something, you know, even through the course of working with him, he initially had better control over his fingers, but then we had to move to a foot pump to better accommodate him. So I think it is a really interesting design challenge. And I think maybe some of that speaks to that the design needs to be able to evolve with people and continue to develop as they move along in their life, be adaptable. Maybe there's many different ways to control the device. If one part starts to not work as well, you can switch it to that way. So maybe it's more of an adaptive device. But that is definitely one of the design challenges I'm looking forward to tackling.